Good morning. So today is June 3, 2020, and our subject is Electric and Electronics Fundamentals 3. For today, we are going to have activity on sinusoidal alternating current frequency measurement. This is the continuation of our previous activity on frequency measurement, but this time we are going to increase the frequency to 100 Hz, and we're going to use the output voltage as 5 volts. This is peak, and this is the frequency 100 Hz. Of course, we're going to use the oscilloscope to measure for time and frequency. So let us try to start. But before that, again, let us review the parameters of a sine wave. So before we measure this peak value, so this is the peak value from this line up to this, so that is peak. And from this up to this point is called peak to peak. So this is the parameters that we measured in our last activity, but this time we are going to measure the time. So this time, by the way, is the time for one cycle, so or period. So from here up to here, that is one cycle. So one full cycle, you have the positive and negative, and this is also called the time for one cycle. So meaning that is the time it takes to complete one cycle. So let's say this is 1 second, and in 1 second there is one cycle, so we can say that it is 1 hertz. So in this case, if when we say 100 hertz, meaning in 1 second, for the period of 1 second, there are 100 cycle or 100 hertz. Again, 100 hertz is the same as 100 cycles in 1 second. So is it clear? So we are going now to measure this time. What is the period for one cycle? So of course, we are going to use again the source of our sine wave alternating current. This is function generator set at 5 volts peak and set at 100 hertz. And of course, this oscilloscope, we're going to measure the frequency and the time. So let's start. So I have to connect this probe to the input of oscilloscope, and of course this one, the ground. So this is now the connection. So output connected to the probe of the oscilloscope. As you can see here, okay, so I will stop. Then as you can see here, the period is, so here, no, the period is, okay, 9.994 milliseconds. So I will write here time, no? Time is, okay, 9 point, okay, 9.994 milliseconds. So here, no, 9.994 milliseconds. And the frequency here, no, the frequency is here. Okay, you can see that the frequency here is 100.1 hertz. So here F is equal to 100.1 hertz. So let us try to draw the waveform just here. So there are 4, then position here. So how many boxes. So there are 2.5 box. So you have here 1, 2, 3, 4, 5. So 3 up, and then 2 B. So this is we are going to draw the waveform. Okay, so it's not that perfect, although this is the period, no? This is the period from this up to this, so 1 to almost 2.5 division. So this is the waveform. And as you can see here, we measured time that is equal to 9.994 millisecond, and then the frequency is 100 Hertz. Now, let us try to compute the frequency using this time, no? This time. So F is equal to 1 divided by time, the formula. So that is 9.994 millisecond, or convert it to seconds, so that will give us 1 divided by 0.0109994 second. So you just divide this millisecond by 1000, so you can convert it to second. Okay. So here, so try to compute 1 over time. So and then convert to second. So that is divided by 1000. 1, 2, 3. So 2 zeros. So then let us try to use our calculator. So that is here 1 divided by 0.009994. Okay, so that is equal to 100 Hertz. So 100.06 Hertz. So 100.06 Hertz. So as you can see in our result, that the computed and the measured value are the same. So we're able to prove that the theoretical and computed value are the same. So thank you very much. I hope you understand our topic for today and try to practice solving the problem using this simple formula. Good day, Group A, C, and D. This is Mr Red.